Welcome. Today, we're diving into the qualifications of clean room airflow, focusing on velocity and pattern. I'm Dr. S.K. Singh, and together we'll explore how these factors ensure the controlled environments critical for many industries. Let's get started. Let's start by understanding why controlled airflow is so important in cleanrooms. Airflow isn't just about moving air, it's about managing contamination. Our main goals are clear. Remove airborne particles, protect both product and process, keep the cleanroom's classification intact, prevent contaminants from migrating, and maintain the right pressure balance. To do this, we focus on key airflow parameters like velocity, volume, direction, pattern, and air changes per hour. The principle is simple. Clean air must constantly sweep contaminants away from critical areas. Let's talk about airflow classifications and why they matter. First, we have unidirectional or laminar airflow. This moves in a smooth, parallel pattern with uniform speed, usually around 0.45 meters per second. It's used in the cleanest environments, like ISO 5 or Grade A areas, where contamination control is critical. Then there's non-unidirectional or turbulent airflow. This one moves in a mixed, random pattern common in ISO 7 and 8 areas. The goal here is to keep particle levels low by diluting the air, rather than relying on steady flow. When it comes to regulatory expectations, airflow plays a crucial role. We're talking about studies that visualize airflow, ensuring it's uniform and free of turbulence, especially in critical zones where products are exposed. This isn't just a best practice, it's a requirement across multiple standards and guidelines. From the EU's GMP Annex 1 demanding unidirectional airflow, to the FDA's call for smoke studies, each authority has its own way of verifying airflow patterns. Together, these regulations ensure the environment protects the product and maintains quality. When selecting airflow velocity, several factors come into play. We need to consider how sensitive the product is, whether operators will intervene, the layout of the equipment, the heat load, and how turbulence might be generated. Choosing too low a velocity risks poor particle removal and higher contamination. Too high, and we face turbulence, particle reentrainment, and disturbance to the product itself. Typical velocity ranges vary. For example, Grade A cleanrooms usually run between 0.36 and 0.54 meters per second, while biosafety cabinets hover around 0.45 meters per second, plus or minus 20%. Let's talk about common airflow problems we often encounter. Turbulence, air stagnation, and recirculation zones can all disrupt smooth airflow. Equipment and even operators can create unexpected obstructions or disturbances. Ideally, airflow should be smooth and parallel, with no dead zones or reverse flow to quickly remove contaminants. To understand and improve this, we use smoke studies. These help us visualize airflow direction, detect turbulence, and confirm that aseptic protection is working as it should. When we talk about instrument requirements, there are a few key points to keep in mind. First, every instrument needs to be calibrated and traceable, and it has to be used within its validity period, no exceptions. For airflow qualification, we rely on tools like hot wire and vane anemometers, balometers, and velometers to measure velocity accurately. To visualize airflow, smoke and fog generators come into play, often paired with video recording systems. And supporting all this, we use differential pressure gauges, particle counters, and temperature and humidity meters to get the full picture. Let's walk through an example of calculating airflow velocity in a laminar flow setup. We start with a measured airflow volume of 720 cubic meters per hour, passing through a HEPA filter that's 1.2 square meters in area. First, we convert the flow rate to cubic meters per second. That's 0.2. Then, we divide this flow rate by the filter area to find velocity, which comes out to about 0.167 meters per second. This velocity is below the required Grade A standard, meaning the airflow protection isn't sufficient. So, further investigation and system balancing are needed. Let's look at an example of airflow velocity that meets the pass condition for a Grade A laminar flow unit. We start with an airflow volume of 1,800 cubic meters per hour and a HEPA filter area of 1.1 square meters. First, we convert the airflow to cubic meters per second. That's 0.5. Then, we calculate velocity by dividing 0.5 by 1.1, which gives us about 0.455 meters per second. This falls comfortably within the required range for grade A, making it suitable for aseptic operations. Now, let's dive into smoke visualization qualification, a key step in ensuring clean airflow where it matters most. We focus on critical observation areas like the filling zone, stoppering area, open product exposure zone, and material transfer points. To capture everything, video recording is mandatory, along with detailed observation reports. The goal: to demonstrate airflow direction, verify that airflow is truly unidirectional, detect any turbulence or dead spots, assess how operators impact the environment, and ultimately confirm product protection. We study these conditions both at rest and during dynamic operation, including simulated interventions and normal equipment function. When we talk about airflow qualification, we break it down into 4 key stages. First, design qualification. Here, we review the HVAC design, run computational fluid dynamics if needed, and assess any risks. Next comes installation qualification, where we verify HEPA filter installation, check instrument calibration, and confirm airflow balancing. Then, operational qualification focuses on measuring velocity, running smoke studies, and testing airflow uniformity. Finally, performance qualification ties it all together with dynamic airflow checks, environmental monitoring, and long-term trend analysis. Each stage builds confidence in the system's performance. Now, let's talk about the additional expectations we have for airflow in critical environments. After any intervention, airflow needs to recover quickly and remain stable. The distribution has to be uniform, no dead spots or turbulence allowed. Operator protection is key, so reverse airflow is simply not acceptable. We measure this with specific criteria, like maintaining a grade of velocity between 0.36 and 0.54 meters per second, and using smoke visualization to confirm smooth airflow. These standards ensure safety and consistency. When things go wrong with airflow, we need a clear plan to fix it. That's where corrective actions come in, like air balancing, replacing HEPA filters, repositioning equipment, or adjusting the HVAC system. Sometimes, we have to repeat smoke studies to see how air really moves. Common problems include low airflow from fan imbalance, turbulence caused by too much air, or dead zones where particles build up. Each issue has a cause and an impact, so troubleshooting means matching the problem to the right fix. Let's look at a real example, an aseptic filling line. A smoke study revealed turbulence right above the open vial filling zone. Digging deeper, we found the airflow velocity was too high, at 0.62 meters per second. Fans were running too fast, and some equipment was blocking the airflow, causing it to swirl unpredictably around the filling needles. By reducing the velocity to 0.45 meters per second, rearranging equipment, and rebalancing the airflow system, we achieved smooth, laminar flow. The smoke study passed, and the aseptic process was successfully validated. To truly prove a cleanroom's performance and ensure aseptic protection, controlling airflow velocity and visualizing its pattern are absolutely essential. This isn't just about good practice. It's about meeting strict standards from organizations like ISO, the FDA, and WHO. Airflow velocity and pattern play a critical role in protecting products, controlling contamination, and assuring aseptic conditions. To qualify a cleanroom effectively, we need precise airflow measurements, proper smoke studies, careful HVAC balancing, and ongoing monitoring and maintenance. This is how we keep everything safe and compliant. That brings us to the end. If you need any further support or have questions, please don't hesitate to reach out. Thank you for your time and attention. It's been a pleasure sharing this with you today.